Welcome to the lecture on fundamentals of MIMO wireless communications. Now we are at the fourth lecture. We begin with a brief overview of what we have seen in the previous lecture and then continue to look at the layered view of communication systems, which will give us a peep into the channels or how we look at the channels from different perspectives before going into the detailed channel models. So, what we have seen in the previous lecture, the last few things that we were trying to see is when MIMO is used in a communication system, especially a mobile communication system or a communication network, we have multiple transmitters enabled with MIMO, and what we would desire is that to exploit the full capability of MIMO, they coordinate transmission amongst themselves. One of the mode could be joint transmission, where they would be coordinating the signals through a central processor and transmitting in such a way that instead of interfering, they get mutually beneficial signals. The next what we saw quickly was they do not have a central joint processor, but they coordinate to use the different MIMO modes so as to reduce interference. The last one what we saw is along with MIMO, they connect to radio resource allocation, that means allocation of resource units to users combined with MIMO mode selection, again through coordination of channel information amongst these base station, however signal processing at the individual base stations. What we were seeing at the last was some of the prerequisites. I repeat, we require a revision of digital communication systems, which we have revised very briefly, so that those who have are not in touch with it are requested to revise some of the concepts. Probability and statistics we will require, like distributions. Linear algebra we will require in this particular course. We will spend a very short while on linear algebra if necessary. The books would be Wireless Communications by Rappaport and Mobile Communications by Gordon Stuber in the initial part where we talk about the channel. The main book of this course would be Introduction to Space-Time Wireless Communications by Paul Raj, and Wireless Communication by Andrea Goldsmith is also another important book which you can use. There are many other books on MIMO communications also, so there is no such restriction in this particular course. Feel free to refer whatever material that is available with you. We would also need elements of information theory, and of course we will present it in such a way that we are able to cover the basics before we go into the details of MIMO communication. We have also listed down some of the important famous researchers in this particular domain, so that you can go to their web page and collect sufficient material which are quite fundamental and which are since the early days of this particular domain. Of course, don't limit yourselves to whatever I am pointing out here. There could be many other resources, so feel free to take as many resources as possible, provided you are able to give appropriate time, because this is a particular subject which has been evolving. A lot of things have been done, and if you would refer to the fundamental works, you might feel more motivated. There might be additional information which you might be able to capture, which goes beyond the limitations of this particular course. This is an important suggestion which I would like to provide, especially on how to prepare. But before we talk about that, this is how it is organized. We have already talked about introduction to MIMO wireless communications today, telling you about the broad overview of how things are. We have revised some of the important assumptions of digital communications, and then we will go into the propagation channel models, because without understanding channel models, it is impossible to design any wireless communication system. We would need information theory for MIMO wireless communication systems. This is also very important. We do not require a thorough understanding of information theory, but we will require some important tenets from information theory. Of course, we will revise them. That will give you sufficient preparation to undertake the results that are very critical for MIMO communication system. Then if necessary, we will look into fundamentals of linear algebra as and when applicable in particular situations. We will study capacity of MIMO communication systems. We would look into diversity mode of MIMO communication system and also multi-user MIMO communication. Now the most important part is how to prepare. I would strongly recommend that read references, especially the ones that have been pointed out, and not limiting yourself to these books. The first 3 references that I have mentioned here are very, very critical. Sometimes this book is also useful. This is quite easy to read. These books are more detailed. So, I mean, whatever you feel more comfortable with, you follow that. This is what we will follow. So, throughout the second half, especially of this particular course, this will be required as a supporting material in the course. So, please read references. I would strongly recommend you should do parallel reading beyond going through these lectures. Work out simulations. So, we will be giving out simulation examples, simulation assignments, so to say, which you should try yourself. And there might be some possibilities of using virtual labs in certain cases, which again would give you some practice and understanding of things. And if it is possible to get a hardware laboratory facility, I would strongly recommend using those facilities. We do have one over here, and I don't know how to extend the facility to the rest of the masses, but if you are attending any course at IIT Kharagpur, you can always come and use some of the facilities here. So this is very, very important to remember. You should read references and you should work out simulations, because without this it is very difficult. Because when we are talking about communications, unlike other domains, this requires a lot of imagination. So you have to be imaginative, because you cannot touch or feel the signals. So and to do them, you require a lot of complex instruments. So imagination is necessary. Simulation is one step beyond imaginations, a little bit closer to what is reality. So if you are able to do that, that would be highly recommended. So with this, we move forward to our next details. So we'll be talking about the layered view of transmitter and receiver, and introduction to the channel. So we have already talked about what we have discussed in the previous lecture. Yeah. So today we'll be talking about the layered view and looking into the channel. Now, why do we have layers or interfaces? Because what we have is very, very complex systems today. If you look at a typical telecommunication network, or the way you access internet, it's like you are mixing a lot of devices, many different devices which operate in various ways. They have various design procedures, and they're really complex to analyze. Now, because it is very, very complex to analyze the performance of such systems, it is important that there is a layering approach, and there is standardized interfaces. So we will see what are these two important things. A standardized interface allows the user or the equipment on one side of the interface to ignore all details about the other side of the interface, except for certain specified interface characteristics. Those who are used to programming, for them the application program interface is one of the things. A very, very simple thing would be like functions. For example, we often use the print function. Right? I'm taking a completely odd example, but you may be used to this print. Print function requires certain input parameters, and it also has an output parameter. We never try to understand the details of the print function. We try to use the print function by its input and output, which are its interfaces. The details of this print function varies from different operating systems and different hardware facilities. So these are interfaces to this particular module or this particular function. So that is what we mean by interfaces. Now, when you have a large number of modules interconnected, if an interface is properly defined, this device need not know about what lies ahead of it. It just needs to talk to this through this particular interface. That's it, nothing beyond. And this device needs to know how it was going to send information to the next one. That's it. And it did not understand the details of it. Only the interface specification is required. That helps us in studying complicated systems. The idea of layering, Again, idea of layering in communication system is to break up communication functions into a string of separate layers. Now, we have already seen the 7 OSI layers. Today we are going to see some other way of looking at communication systems. Yeah. So, we now move on to look at the typical block diagram or typical structure of how this layering concept is used in a communication system. So, we have already drawn in the previous lectures the input that comes into the system. Let us say there is a module which we call as input module I. It has an interface to the input module I minus 1. So, this is the interface between I to I minus 1. This goes on and on until we are at the last stage, which is the input module 1, which is the last module of the transmitter. From this, the signals go in to the channel. From the channel, it goes in to the receiver, or we can also call it the output module 1. There is this interface. Corresponding to each module at the transmitter, there would be an output module at the receiver, and this is also I minus 1, and there is this output module I. So, this is the interface from I minus 1 to I minus 2, right. Signals flow between these interfaces. This and these are peers. This and this are peer of each other. Again, this and this are peer of each other. So, when this input module sends a signal, it needs to know this particular interface or in what format data will be received by the next module. Similarly, the corresponding output module needs to know in what format it should give data to the next higher module, so that this is able to process. This module did not know what goes on in details in this particular module. If we take the exact look instead of this particular abstract look, what we have is again the same picture what we had seen earlier. The source sending information to source encoder, source encoder sending information to channel encoder, channel encoder sending signals out into the channel, channel feeding information into the channel decoder, channel decoder giving it to the source decoder. This is the destination. Now, if we look at these interfaces, this interface could be analog or it could be digital, depending upon the source or the destination. This particular interface is usually a binary interface. moving ahead further, if we try to expand only this particular section of the communication link, what we will get is, I will write in short, input, let us say waveform going into the sampler, into the quantizer, then to discrete encoder, followed by the decoder, table lookup, analog filter, and of course output waveform. Interestingly, what we can say is, in this section, that means what goes out and what comes in, we can refer to this entire part as a channel as being viewed by the discrete encoder and the corresponding discrete decoder. Whatever distorted signal it receives, it is because of the channel that the encoder and the decoder experiences. Now, these would be encoded signals. So, one encoded or the code could get modified to another code because of the channel characteristics. So, here this particular interface, as you have seen here, is a binary interface. Therefore, the channel that it would see is a binary interface again, and therefore, the channel would be a binary channel in this particular case. This particular interface is basically a symbol sequence, and if we take this portion out and we are talking about the quantizer and the table lookup only, the channel would appear as a symbol input, symbol output. So, symbols would go in to the channel, symbols would come out. The job of this module at the receiver would be to generate whatever was available here at this point with minimum error. If we look at the sampler and the analog filter, and we try to see the system at this perspective, that means, if I block out this and see sampler is sending something into the system and the system is giving out which is to be filtered. So, basically what we have is an analog sequence. Therefore, the channel at this point is again an analog channel. So, basically what we can say is, it depends on from what is your perspective or which part of the communication system are we looking at. So, the channel will get a representation accordingly. If we move further down beyond what we have discussed and go into the details of the channel encoder, let us say, if we are expanding the channel encoder, so what we can have initially is the cyclic redundancy check at the transmitter, then we have the forward error correction encoder and interleaver. In this time we are grouping them together, followed by symbol mapping, followed by D2A. We would be reducing some of the components for the sake of discussion and ease, followed by high power amplifier and RF section, etc., and then the antenna. from the antenna we have always written as the channel. At the receiver side, we again have the antenna followed by the RF section of the receiver, followed by A to D converter. Again, we are not following exactly all the components because our interest is something little bit different in this particular lecture compared to what we have discussed before. So, this is basically the demapper, followed by the decoder, and then there is this CRC check. Here you get packets as input, here you get packets as output. If we start to take a look at this channel, that is the actual channel what we usually talk about, what we have is basically the RF channel. It is very important. We have the radio frequency channel in this section, so it is dependent upon the carrier frequency of operation. For instance, if we are talking about let us say few hundred megahertz, the channel properties would be different. If we are talking about gigahertz range or millimeter wave communication, the channel properties would be different. So, basically at this point it is the RF channel what we are considering. If we move down a little bit and take this section, so that means we will not model the RF part as typically in a digital communication system we do not do, but here at this point, since we have baseband analog, therefore we can say we have a baseband analog channel. That means analog baseband signals are going in, analog baseband signals are coming out from the channel. Now, if we take a look at this section, what do we have is discrete samples, that means discrete in time and continuous in amplitude. So, here also we are going to get a baseband, but discrete time analog input and output as the channel. So, at this point we will not be concerned with D2A and A to D or the RF section, everything is captured in this part. Most of the channels which we encounter in our systems of study is at this interface. So, what we have is symbol mapped, that means let us say constellation points going in. What comes out is another signal space, that means probably if I take QPSK constellation, this goes into the channel, let us take this point going into the channel. What comes out from the channel would be, if this is my reference point and this is my signal space, what comes out from the channel could be anything which is there, or it could be directly on top of this, or it could be here. So, the received signal is on this space. If we move a little bit left, this is the binary interface. Now, this binary interface is little bit different from the other binary interface that we have said. So, this is also a binary channel. So, we can say it is a binary channel, but when we look at this, the typical performance metric would be probability of bit error. Okay, probability of bit error of uncoded systems, because in this section there is no error correction coding being taken into account. Most of the performance analysis we do is in this part of the link. That means, we will take discrete time samples of the channel or the waveform channel, this is also known as the waveform channel interface, and we might be studying error probabilities of the link at this point. When we move down further, here again it is a binary interface, but here the probability of error is different compared to the probability of error at this point. So, definitely what we can see, or what we know, if probability of error over here is around 10 to the power of minus 3, the probability of error over here is going to be 10 to the power of minus 4. So, although this is a binary interface channel, the error probabilities or the channel properties are different at this point compared to this point. So, what I am trying to say in this picture or through this explanation is that it is very important to see in which part of the communication link or which part of the physical layer we are located, and what kind of interface are we doing with the channel. The last thing that we can see, suppose we are seeing things from this point, it is again a kind of binary, but here what the channel would be kind of packet error probabilities. So, instead of a bit going into error, here what we will be getting at this interface is a packet going into error. So, packets would be sent into the channel and packets would be received from the channel, or we will be getting values what is the probability of the packet being in error at this particular interface, and we can encapsulate everything that lies on the right hand side. In this particular course, we will be mainly concerned with this section unless otherwise specified. This will be our most important part that we are going to cover in this course. The different kinds of channels which you may have seen till now, or if we try to write down the typical channels which you may have come across or which you may come across in future are, first we would try to write down the binary channel. In the binary channel, it could be a symmetric channel, it could be erasure channel, it could be instead of binary, it could be a symbol level emery channel, which could again be symmetric or asymmetric. We could have non-ideal channels. Sorry, before that I would like to write we have additive white Gaussian noise channel. Then we can have non-ideal channels. Then under non-ideal channels we could have linear time invariant systems, and we could have linear time variant channels, and of course we can also have non-linear channels. Typically in digital communications, one encounters additive white Gaussian noise channel or a binary symmetric channel. Sometimes people come across erasure channels, and on rare occasions one would come across emery channels. So, these channels are usually also referred to as waveform channels, whereas these are binary or probability based channels. In our communication systems, we would be using mostly linear time variant channels. In wire line systems, one would encounter linear time invariant channels, but in wireless communication systems we would be usually encountering linear time variant channels for reasons what we will shortly see. In the next lecture, we will be talking a little bit more details about what kind of time variant channels are usually available and what are the different kinds of models, what are the different kind of features, and why do we need to study the channels and what is the importance of studying these channels. Thank you.